When enterprise AI systems collapse, they almost never do it in the laboratory. They break upon contact with reality. In 2024, the RAND Corporation conducted structured interviews with 65 experienced data scientists and engineers to measure the gap between what AI can do in optimal conditions and what it actually achieves in production. This chart illustrates their findings. We expect complex IT projects to fail at a baseline rate, but the AI project failure rate surges past 80%, double the failure rate of IT projects that do not involve AI. The root cause of this failure rate is architectural. Look at this tightly clustered data. This is an evaluation distribution. Models are optimized to perform well on these specific benchmark tests. But the pristine, predictable queries a model is evaluated on almost never match the chaotic, ambiguous inputs that actual users submit in the real world. When the system goes live, production queries scatter wildly outside testing parameters. The deployment distribution rarely aligns with evaluation. In high-stakes domains like medicine or law, the consequential queries are extreme outliers, sitting furthest from familiar training data. Achieving flawless performance on a benchmark is a mathematically useless metric if the architecture shatters the moment a user asks a question the system was never designed to answer. When these deployments inevitably fail to meet expectations, organizations have to determine why. The default professional response across stakeholders and engineering teams alike is to point at the generated output and conclude, the AI made a mistake. Attributing a system failure directly to a model failure is a diagnostic error. It assumes the raw model is the entirety of the system, rather than just one component within it. Because the organization blames the model, they seek out a model-based solution. They rip out the current language model and replace it with a newer, theoretically smarter one, hoping the next version will finally understand what went wrong. Swapping models without altering the surrounding deployment architecture accomplishes nothing. It simply reproduces the exact same failures under a different vendor's name. Deploying AI responsibly requires abandoning the hope for a magically flawless model. The discipline lies in building a surrounding engineering architecture that compensates for the model's known limitations. To build that architecture, we first have to acknowledge the reality of the core model. A raw language model has absolutely no inherent concept of truth as a target. It optimizes entirely for statistical plausibility. That pursuit of plausibility comes with distinct constraints. First, the context window attends unevenly to the information you place inside it, often missing crucial details hidden in the middle of a prompt. Second, the standard retrieval system is designed mathematically to find similar documents, rather than documents that are logically relevant to the user's specific query. Third, embeddings capture distributional proximity, rather than actual semantic meaning, and the attention mechanism assigns weight to tokens without actual comprehension. Fifth, the fine-tuning process is highly effective at modifying how a model behaves and sounds, but completely unreliable for permanently updating its factual knowledge. For a rigorous breakdown of exactly how these mathematical constraints operate at the code level, you can read the complete 7-part series on Medium. Taken together, these constraints mean the core model is epistemologically indifferent. It cannot distinguish between what is true and what sounds true, which makes it mathematically incapable of self-regulating its own outputs. If the automated system is mathematically indifferent to truth, the responsibility for verifying that truth falls entirely on the human beings operating the system. This dynamic is mapped out by technology scholar Madeline Eilish as the moral crumple zone. Her research demonstrates how human operators are routinely forced to absorb the legal and moral blame for automated failures, even when the software design gives them no actual control over the system's decisions. We expect automated intelligence to behave like human intelligence. A human expert who doesn't know an answer will hedge. They will express uncertainty. They will ask for clarification before offering advice. An LLM defaults to the exact opposite. If it lacks the answer, it confidently generates a fluent, highly structured lie, presenting it with the exact linguistic certainty of a verified fact. Deploying a naked language model without structural safeguards does not solve a business problem. It actively creates a liability problem, shifting the cost of failure directly onto defenseless end users. Building the outer loop surrounds the model with 4 critical functions. First, a failure taxonomy, red teaming actual queries. Second, retrieval provenance, tying outputs to verified documents. Third, scaled oversight, routing high-stakes queries to humans. Finally, continuous evaluation infrastructure to monitor data drift. True epistemic responsibility exists only when these 4 external layers actively intercept, diagnose, and correct model errors before a human being is ever exposed to them. The technical architecture of the outer loop is solvable. The primary reason responsible AI fails is organizational. The hardest part is surviving corporate pressure. The engineers who rigorously test a model and understand its failure modes in depth rarely hold the authority to make the final deployment decisions. The philosopher Michael Polanyi defined this gap through the concept of tacit knowledge. He summarized it with a simple phrase: "We know more than we can tell." Look at this organizational chart representing a system handover. When an AI project moves from the original engineers to the operations team, the final configuration values are strictly documented, but the tacit knowledge, the reasoning behind those choices, evaporates. The new team inherits the final code, but they lose the entire history of what the previous team tried, what failed, and why certain architectural alternatives were discarded. Losing the history of what doesn't work leaves future operators completely blind to the system's actual boundaries. They are forced to manage a fragile architecture without knowing where the load-bearing walls are. To prevent this structural collapse, engineering teams must formally write down their discarded architectural alternatives. Preserving the record of failure is just as critical as shipping the final product. Which brings us to a final diagnostic test you can run during your organization's next engineering handoff. Ask the team in the room to identify 3 specific configuration values in the current deployment that nobody at the table can fully explain. If that number isn't 0, your organization has not engineered a responsible AI system. You have merely deferred the inevitable discovery of your failure modes to your users. For the complete architectural framework, including how to allocate responsibility across the retrieval, evaluation, and oversight layers, read the full series linked below. The question is no longer whether we should trust AI. Responsible deployment is knowing exactly what outer loop systems you have built to catch the model when it falls.